We want to see how we can apply what we learned about thermal and applied load deformations. Let's consider a system of 3 steel pipes, where a modulus of elasticity is given as 30,000 ksi, and it's loaded and supported as shown below. We want to determine the change of length of the complete system for the 3 configurations. The first configuration, A, is if our cross-sectional areas of pipes AB, BC, and CD are given as 1.200 inches squared, 1.000 inches squared, and 0.800 inches squared, respectively, and the only thing we are considering is the applied loads at the rigid plates B, C, and D. The next configuration we want to consider is if the unloaded system, i.e. there are no applied loads, experiences a change in temperature of 300 degrees Fahrenheit, given a coefficient of thermal expansion of 6.94, 10 to the minus 6 inch per inch degree Fahrenheit, and the last configuration C, considering both loading and thermal effects. For us to begin, we first have to determine the internal reactionary forces of each member, such that we can determine the local deformation. From the figure to the left, we can conclude the following. If we cut member CD anywhere between our 2 rigid plates, we see R1, our internal reactionary force, has to be equal to 15.0 kips, and this member is going to be in tension. If we cut member BD anywhere between B and C, we see that R2, our internal reactionary force, has to be equal to 20.0 kips, and this member is also going to be in tension. Lastly, if we cut member AD anywhere between A and B, we see our internal reactionary force, R3, is going to be equal to 10.0 kips, and this is going to be a compressive loading state. The total deformation for the rod system due to our applied loading is given as delta is equal to sum from I is equal to 1 to n of R sub I, L sub I, per E sub I, A sub I. Now n is going to be equal to 3 for our 3 unique segments. Thus, we'd have our first segment that's going between C and D, where our internal reactionary force was 15.0 kips, our length was given as 20.000 inches, our modulus of elasticity is given as 30,000 ksi, and our cross-sectional area is given as 0.800 inches squared. Now we will add this to the deformation of member BC, where our internal reactionary force was given as 20.0 kips, the length was given as 16.000 inches, our modulus of elasticity was given as 30,000 ksi, and our cross-sectional area was given as 1.000 inches squared. And lastly, we will subtract the deformation of member AB, for that is a compressive state. Our member is going to decrease in length. Thus, we'll subtract the quantity 10.0 kips times a length of 14.000 inches per a modulus of elasticity of 30,000 ksi times a cross-sectional area of 1.200 inches squared. And we find, due to our applied loading, the total change of length is a positive 0.0193 inches. To determine the deformation due to thermal effects, delta T, we have to sum from I is equal to 1 to n of alpha delta T L sub I. Now, the coefficient of thermal expansion for all 3 members is the same, 6.94 10 to the minus 6 inch per inch degree Fahrenheit. Our delta T is the same for all 3 members, 300 degree Fahrenheit, and thus we just have to multiply this by the sum of our lengths. 20.000 plus 16.000 plus 14.000 inches. Thus, our total thermal deformation is 0.104 inches. Lastly, the total deformation due to thermal and loading effects is just the sum of our respective terms from part A and B. Thus, delta total is equal to 0.0193 plus 0.104 inches, where 0.0193 is our deformation due to our applied load, and 0.104 inches is due to our deformation of our thermal effects. Thus, our total deformation is 0.123 inches.